Я думаю, что презентовать буду на английском, потому что презентация на английском, и плюс для Жабира, я так думаю, что лучше будет, нет?
As you want.
As you want. Okay.
Не, ну, конечно.
Ну, вы можете по-русски говорить, поскольку презентация английская. Ну
Он
ладно,
и
это,
говорит,
в
что
общем...
из его
Не, как вам будет удобно, просто могут возникнуть еще проблемы с терминами.
Наверное, слушателям, наверное, все равно.
Ну да, тут вот даже вот название переводить по-русски уже как-то искажается. Понятно. По-английски лучше звучит.
Хорошо. Но вопросы в любом случае вы можете задавать на русском. Я буду отвечать на русском, как будет удобно.
Да.
Сейчас, нет, у нас еще появился один слушатель, не русскоговорящий, так что все-таки на английском в любом случае.
Окей.
Ага. Ну хорошо, значит, вот я просто представлю, да. Я куда-то вылетел. Сейчас. Меня слышно, да?
Да.
Слышно?
Да.
Я, например, никого не слышу.
Слышно.
Все, нормально. Ну вот, значит, у нас сегодня доклад Ашота Алексиана. Вот, значит, exit problem for SID, как он сокращал так удобнее, SSD, diffusion processes. Вот, но переводить я не буду, это вот эти сочетания, они как бы по-английски лучше звучат. Вот, и, значит, это содержание, как я понимаю, его диссертации, которая в скором времени предстоит защита. Да, пожалуйста, Аша, давайте начинать.
Thank you. I will present in English. So thank you very much for having me. I haven't done presentations in Paris School of Economics for a while. And I have never presented my own work. So thank you for having me today. The topic of presentation is exit problem for self-directing and self-stabilizing diffusion processes. This is the topic of my thesis that was done under the supervision of Aline Kursman from University of Lorraine and Julien Turgot from University of Saint-Étienne, Jean Monnet University. So first I will present you what constitutes exit problem. What does it mean to solve an exit problem for a diffusion process? I will use the example of Ito diffusion process because this is the basic one. Then I will make a small introduction to the models that I will consider in this talk and that I considered in my thesis. These are self-interacting diffusion. It is the diffusion process where you have interaction of the diffusion with its own path. And self-stabilizing the diffusion, also known as the McKean-Vlasov process, but a particular version of a McKean-Vlasov process. So you have interaction with the law of the process at each point of time. So then I will talk briefly about the state of the art and what was done for exit time problem for these two processes. Then the goal of my study and what we achieved. Okay. So what is the exit time problem? You can think of it the following way. You have a domain in your space. It can be RD. You have a diffusion process that is wandering in this domain, and at some point it touches the boundary of the domain. This exit time tau g sigma is the first time. It's a stopping time normally if xt is a good diffusion process. Yes, so the goal is to estimate this time. We are interested in a particular version of exit time problem. It should be an exit from a stable domain of attraction. So the domain itself, it should attract the diffusion process inside. The exit should happen under the influence of Brownian motion. So, and we have a parameter sigma that regulates the strength of the Brownian motion. When it goes to 0, then we don't have a lot of movement along the deterministic path, and we are interested in this behavior, in the behavior when the probabilistic effect is very small. So we are interested in the exit from the stable domain, but against the lines of the gradient field. Okay. So the normal assumptions are here. There should be one attractor within the domain G of the potential V. G should be normally bounded, and it should be stable, which means that wherever we start inside the domain G, we should converge towards this one attractor. So for the diffusion, for eta diffusion processes, this exit time problem is known under the name of Freidlin-Wentzell theory, which was done by Freidlin-Wentzell in the 70s. Here, as literature, I give their book of 98, but the work was done in the 70s. So this is eta diffusion. We have a normal diffusion process. As you remember, we assume that we are inside the stable domain G, which means that there is only one minimizer of the potential V inside domain G. And yeah, these are the assumptions. And what they say is the following. This is the normal picture. We have the gradient field that is attracted towards A. So if sigma is very small, then your particle following the lines of this gradient field, it converges towards A. It stays there exponentially long time before exiting the domain. So this is what is written here. For any delta that is greater than 0, your exit time is between exponential of some rate h, where this h is the height of the domain, height of the potential within the domain. Okay, so it is infimum of the points v of x along the boundary of the domain. It's the height of the potential within this domain. Okay. So naturally, if sigma goes to 0, this guy goes to infinity, this guy goes to infinity, and we say that exit time behaves exponentially with the diffusion term going to 0. So now let me introduce you to two diffusions of interest that I considered in my thesis. First one is so-called self-directing diffusion.
Okay, let me make a remark, because I know this story from the very start. And you may be interested to know what is actually the problem. This problem was proposed by David Williams, who I know him very well. He is alive still. He's a first-class mathematician who took over the statistical laboratory from David Kendall. And what he actually wanted, he wanted to approximate not intersecting Brownian motion, okay, in potential. But this, so he wanted to consider singular potential as a point zero. Okay, the more and more singular potential, such that the potential prevents the particle to intersect itself. Okay.
Okay.
But it turned out to be extremely hard problem, and they were not able to solve it. The problem is still open. And instead of this, many people, including yourself, started to consider smooth potentials. So the initial problem was to consider potential which is singular zero, okay?
Okay.
Or a sequence of such potential. But this is a difficult problem. It was abandoned, and you may be interested to know this facts. Okay.
Okay. Yeah. Thank you for the remark. It is true that the techniques of Freidlin and Wentzell and our techniques as well, they don't work if the potential is singular. It is different. Yes. Yeah. First, I present self-interacting diffusion process. You see here we have our, I don't know if you can see my mouse, but here we have the drift term, and here we have the diffusion term. In the drift term, it is a normal, we have a normal part which governs the general geometry of the space. But also we add another term, which we call the interaction term. And here the interaction is taken with respect to the previous path of the process via the occupation measure. What is the occupation measure? It is really here. The occupation measure is, so basically what we take is that we take the path of the process, we follow it using the delta function. We have this path, we renormalize it. This is our occupation measure. Actually, we can rewrite this form in another form that is easier to understand. It's this one. So at each point of time, what we do is that we integrate our xt along the previous path using the interaction potential. And this is our interaction term. Now we have to renormalize it such that so that the interaction will not grow with time. And that's it. So you can see it on this picture. At each point of time, we are influenced by the Brownian motion, of course. We're influenced by the general geometry of the space, and we are interested by we are influenced by the previous path.
Okay, I have a question is, can you actually prove that the system without Brownian motion for delta equal to 0 has an attractor? It should be a theorem. It's not a difficult theorem, you see. I can explain you how to do it.
To prove what exists.
It should be proved, actually. It's not that the system without diffusion part has a unique attractor, and I look through your papers, and you postulate it. It's not that should be postulated. So it's a simple theorem that should be proved under some mild condition of potential, and I explain you how to do it. If you delete Brownian motion, you have a simple equation. You put some constant. You have here, if you put fixed point, you have gradient of f of 0. Okay, so you have equation gradient f of the stable point equals minus gradient of f, and it's simple. It's not rocket science. It's simple exercise to prove that after some natural conditions, it has a unique solution. Okay, the unique stable point should be proved. This is exercise, actually. It's not a good idea to postulate existence of a single point as you did. Okay,
I think you know what assumption you are referring to. I will...
you see, your equation for stable point, it's it's basic stuff. If you put fixed point here, delete the diffusion part, then you have simple equation minus gradient v from a fixed point. Okay, suppose I remember you denoted m. Okay, I looked through the paper and it was denoted, I believe, m. So
In the first paper it was m, in the second one it was
equals minus gradient f of 0, you know, and after simple conditions, it's exercise in the calculus.
Yeah,
To prove that under some conditions, it has a unique fixed point, okay?
We will come to this equation. I will explain that not only you should know that you converge to this, to the...
Okay, but it should be proved, and this is not a big deal to prove, that the dynamic without noise has a unique fixed point, okay?
Yeah.
Carry on, thank you.
Just I wanted to say that we will come to this assumption, but you should also know that the trajectory without the diffusion, without the Brownian motion, you should not leave the domain. So you still have to assume
Of course. This is okay. That is not an issue. The issue that I try to attract your attention, but there should be a lemma, which is not difficult.
Okay.
The dynamic without noise has a unique fixed point. Okay.
Yes,
that is something that should be easily done. Okay. Thank you.
Okay. So yes, we have self-directing diffusion. These are the processes that are studied, I think, since the 90s. There were works by Benaim. For particularly this diffusion process, we have global existence and uniqueness in the paper of Klepsen and Kurtzman of 2010. And so they prove it for V and F that are uniformly convex.
Okay, and I don't think that I think the double well potential is also not a big deal. If V is not convex, I think this is done basically.
Yeah, in our second paper we don't prove it, but we refer to. So the only problem that you can have is that it explodes in finite time. If you have convexity at infinity for the confinement term, this problem you don't have. So this is it's true that it's not an issue. It was not it was not the problem that they considered in the paper Kurtzman and Klepsen 2010. The goal was not to show uniqueness and existence. The goal was to show this theory. The goal was to show long-time behavior result. So they proved there that there exists rho infinity, which is a measure that is a unique solution of this equation, to which our occupation measure converges. Occupation measure, if you remember, it's the measure that stores the past trajectory process renormalized with. Sorry, yeah, I think it's not a question. No? Yes. Okay. Yeah, so this is they showed their long-time behavior for the occupation measure of the process. Now let's talk about the second diffusion process of interest. That is self-stabilizing diffusion. As I told you, this is a type of McKean-Vlasov process, and it looks the same as the previous one. That's why I studied them at the same time in my thesis. But here you see in the interaction term, instead of the occupational measure, we have the law of the process. So in some sense, self-stabilizing diffusion should be easier, because in the previous case, mu as sigma was random. It depended on omega, okay? But here it is not random. It is defined when you define the solution to this equation.
Okay. But you also could have a local time, and it would be the same, yeah, more or less. The local time, yeah. Not the law, but local time, yeah.
Local time where instead of
local time is you had the formula on the previous slide for local time. Okay, okay, carry on. Yeah, I understand.
okay. So yeah, so this is self-stabilizing diffusion process. You have in the interaction term you have the law of the process. So now let's see what was proved for exit time problems for these two diffusion processes. So first, let's start with self-stabilizing diffusion process, which is McKean-Vlasov. I will remind because the names are too similar.
Okay, one more remark. If you try to speak English, the English standard is C instead of K for Kramers, and you put a something U over E. Okay,
yes.
So it's not English way. I'm not fluent in Swedish, but I don't think this is Swedish either. The English standard you put C and put a something U over E. Okay.
I think it's the problem is that these are two different grammars.
Okay, Kramers in English. If you want to put papers in English, you put C in English and put accent U over E. So then it would be in English way.
We follow the names.
That's not correct. I know the British standard. The British standard is Kramers with C and accent U. Okay, carry on.
So in the paper of Herman and Keller-Petman that we follow the notation of, it was written with K. So I guess it is either a different person with it's a Kramers with K, or it's them to blame for the mistake. Yeah. So first. Yeah, so the first paper, it's the paper of Herman, Imkeller, and Petman that was done in 2008, where they studied self-stabilizing diffusion process. Actually, they started by considering them in general case, so they did not assume that V and F are convex. The assumptions were different. For this, they showed existence and uniqueness of the process. Then they proved the large deviation principle for this process, and then they realized they cannot prove exit time in general case. So they said, okay, V and F will be convex, and they proved exit time for V and F to be convex. This is what we call convex-convex case. Convex case is simpler than the general one because here we have only one point of attraction. And here you know that your law of the process will be stabilized around this one point of attraction.
Okay, so do I understand correct that convexity of V is not essential, but convexity of F is really used, seriously used, yes?
I think that the convexity of both is essential for the proof.
I don't think convexity of V is a great deal.
Convexity of V is a great deal because they want to control the law of the process forever. And if you have multi-well potential, actually after exit time, your law will not be around your point of attraction within the well that you consider.
Okay, it means that whether you have unique invariant measure for diffusion or you have several measures. If it's convex, you have unique invariant measure. If it's not convex, you have several measures. But this is, I believe, not a big deal. Okay, so thank you.
No, this is a big deal for the techniques that they use, because for them they not only control the law of the process until exit time, they just say that the law of the process will be close to Dirac delta at the point of attraction forever. That's why you need convexity. Because if you have multi-well potential, this is not true. You see, we will talk about it when I come to the exit time problem to our results. Okay. So paper of Herman and Keller-Pittman, they proved Kramers type law in the convex-convex case. Then the second work was done by Tugo in 2016. He did the same thing, but with the same assumptions. But what he did is that he avoided using large deviation principle. Instead, he considered coupling methods, and he controlled the law using different techniques. So that's I will present very briefly right now after finishing the state of the art. So then he proved also for a bit more general case. A bit more general case is when you have double well potential, exactly of exact form. So it's not very general. And then F is convex, so concave, and V is precisely double well potential of a specific form. And the general case, what we mean by general case is that V should be multi-well function. F should be whatever you want, like it should be, it's better for it to be concave, because if it is concave, then we have repulsion. And this is much more interesting case than it is convex, because if it is convex, it's attraction. With repulsion, you have, normally you should have the exit time that is lower, because it should be easier for particles to escape from the domain of attraction. And when it is attraction, it should be harder. So we are actually interested in repulsion.
Yeah. Actually, I agree with you, because in the original problem, F is very strongly repulsive. You should have singularity to the origin. The original problem that was posed by Williams, F should have singularity.
Yes.
But this is still open, I believe. It's not
I also think so. But we can talk about it afterwards, because I think this singular case is it is very hard. Especially you have to control that the singularity of F should not overcome V, because or else your particle will. I mean, it's hard. I think it is hard. Probably you will not have even exponentially big time. It will be something different. But let's talk about it in the end. Yes. So this is this state of the art of self-stabilizing diffusion processes. Up before my thesis, the general case was an open problem. For self-interacting diffusion process, they were just no results. No one could consider exit time for this kind of diffusion. So let me briefly tell you how what was the proof of Tugo to show exit time for self-stabilizing diffusion for McKean-Vlasov one. From the domain of attraction in the convex-convex case. So these are the assumptions that he used. V and F are regular, of course. Gradient V and gradient F are religiously continuous, of course, and not them, but V and F should be convex.
Now, moreover means with probability 1. What means moreover?
Where?
Probability 1. Moreover. What do you mean by moreover? With probability 1?
Where here? Let me finish the assumption. I will come to lemma. So the gradient F is rotationally invariant. This is what was used in Herman and Keller-Pittman to show existence and uniqueness of the process. Then G is, of course, the bounded the domain that is stable under our field. And we have only one unique minimizer. So the first thing that he proved is that yes, because it should be, yes, I see what you mean. It should be expectation here. But this is I think this is the problem.
You mean expectation or with probability 1 expectation?
Yeah, it should be expectation. It should be expectation.
That's sorry.
Yeah, it disappeared somewhere. It should be expectation. So the first lemma that he proved is that you can control the moments of the process, and you can control them after whatever order you want. Okay, so he introduced the time t rho sigma. This is the first time when your moment of order n comes close to a, let's say. Okay. and he proved that it happens in the time that you can control. And moreover, after this time, you will still stay close towards this point. He used basically a convexity argument for that, and a little bit of calculus. Okay, so we have control of the moments of the process after some time that we control. Moreover, he said, so let's observe the following thing. Our gradient f is assumed to be at most polynomial growth. So we don't need to control all the moments of our process xt. We just have to control them after until some order r, which is the order of the polynomial that bounds the gradient f. Okay, this is what is written here. The only thing that we need is to control the moments of xt up to a fixed order r. Then we can control the interaction term in the following sense, that the supremum over whatever compact set you take of this guy, of the difference between these guys, is bounded by a function that can be expressed only in terms of the moments of order 1 and moments of order r. So if they're close to 0, then this guy is also close to 0. So after that, he introduced the coupled process. The coupled process is the one where we know that your unique attractor is A. You know that if sigma is small, you will be most of the time around point A. So probably, and it will turn out to be true, the law of the process should be close to delta A, to direct delta at point A. So let's just put the delta A here. So this is now an eta diffusion, and we expect our process to be close to eta diffusion. So how do we prove it? We just take the difference, we take the square of the difference. Now the Brownian motions, they cancel out because this is synchronous coupling. Then we just take the derivative. We take the derivative, we derive, we use convexity one more time, and we get this.
Okay. Again, you mean the moments, yeah? Or you mean trajectories? What is you mean? You want to say there is expectation, or you consider trajectories?
Trajectories, yes, it's for any omega, because your just cancels out. So now you can take the derivative. Okay. It's differentiable now. And now your difference, it decays after until some level, because if xi becomes too big, this guy is big, so it is negative, so we should decrease. So we have control of the distance. But this guy beta, as we know, with sigma goes to 0, it is small, because the moments of our diffusion are close to A, as was proven in the lemma. So actually we can show that the distance between xt and yt does not go further than some level that is controlled in terms of sigma. So the smaller sigma is, the closer the two processes are. And if the two processes are close, then their exit time should be the same. So this is what is written here. It's the coupling methods. We used to say that the two processes are closed until are close to each other until the exit time, and then he got the exit time. The exit time for our process of interest should be the exit time for the corresponding eta to diffusion, which is of this form. Now H changed, because there, if you remember, instead of V, we had V plus F of x minus A.
Okay, do you assume here that minimizer for H is unique, or maybe several minimizer for you?
For G, yes, the minimizer inside
G should be unique, definitely, I'm sure.
Yes,
the infimum should be taken in one point, yes?
Infimum?
Do you mean that minimize, well, you have the formula H is infimum of some expression.
The measure of this guy. No. It's not.
Oh,
It
maybe
may not be
several.
unique. It may be several. Yes.
Might be several.
Yes, it may be several here.
Okay.
It's not a problem.
Okay. Okay. That you need something to prove because you see you have two tunnels of the similar capacities. Okay, a particle in principle can hesitate which way to go.
It's not a problem.
Some time between these two paths before it will stick to some direction. So it should be proved that this is negligible correction in the exit time. Okay.
No, it's not a problem for the exit time because in Freidlin-Wentzell theory,
it's not trivial. It's not trivial. It's a unique point. So no question asked. That's clear. If you have more than 2 points, then in principle, the particle may spend some time before it will select which path to follow, and it should be proved that this will not contribute for the exit time. Okay, this is something to prove.
Here, it's not a problem because in the Freidlin-Wentzell theory, you can have on the boundary of your domain several infima.
Okay.
For them, it's not a problem, but here you use
let's set with a constant value of H. It's also fine for you, yeah. If you have a continuous set with a constant value of H, that's no problem for you. Okay, so part of the boundary H is the constant. Is it a problem for you or not a problem?
I think it's
not the whole part.
Because I will tell you why it's not assumed in the Freidlin-Wentzell theory, and here you just take the coupling of two processes.
Right. So you're saying that it's possible, yes?
I think it is possible.
H is constant on the part of the boundary. That's no problem for you, yes?
I think it is possible. I think it is possible.
No
you sound very.
It's absolutely to check.
Yeah, we can check. But if it is, so here the proof is very simple because we just take coupling of the two processes. Whenever corresponding Ito diffusion leaves the domain, our process also leaves the domain. Okay. If in Freidlin-Wentzell theory it is possible, here it is also possible because we don't consider anything other than
the time. Okay, but we'll leave at this point. But you understand that there is some question that may be asked. Okay, thank you, Karel.
Okay, so let me do the summary of this proof. For how long do we have the seminar? By the way, it is 1 hour 30 minutes.
Полтора часа.
Okay. So let me briefly show this summary of the proof. So lemma and thus convexity was used to prove the first convergence towards the point A, our unique attractor. The same lemma and thus convexity was used to control the interaction term. If you remember, we took this supremum over compact set. And the closeness arguments, the derivations that we did between y sigma, the corresponding Ito diffusion, and our process, was used to establish the exit time. And here we also used the convexity. So the goal of my project was to, well, first simple task to do the same for self-interacting diffusion, where we have interaction with the previous path. Then think about a general case. Maybe we can do it for self-interacting diffusion, but then if we can do it for self-interacting diffusion, we should be able to do it for self-stabilizing as well. So I just remind you how both diffusion look like. They look like this, except that mu t is different. For self-interacting, mu t is the occupation measure, integral over the previous path, renormalized with time. For self-stabilizing diffusion, it is the law of the process. So we expect the proofs to look similar. We should somehow say that wherever in the domain you start with, you converge towards points of A in constant time. Then your interaction terms should stabilize such that instead of mu t, you can put delta A, because most of the time your process is around delta A. And then it should exit the same way as the associated eta diffusion process, for which we know exit time due to Freidlin-Wentzell theorem. So the first case that we considered, it was self-directed diffusion in the convex-convex case. So basically what we did is that we wanted to follow the steps of the paper by Hugo of 2016. These were our assumptions. V and F are considered to be regular. They should have at most polynomial growth. F should be rotational invariant. V is uniformly strictly convex. This is the case of where we have only one point of attraction. And its global minimum is in our point of attraction. And F is also uniformly strictly convex, which means that we are attracted to our previous path. Yes, here this is the assumption that we were talking about in the beginning, that we assume that the domain G should be stable under this this field, which means that wherever we start in the domain G, under the dynamic, we should still converge towards the point A.
This should be proved actually. There should be a kind of lemma that proves this statement. Okay, that's my remark.
So let's follow the logic of the paper that I presented before. And do we have first conversions towards A? It is actually simple to show that if sigma is small, we will follow the deterministic dynamics. If the deterministic dynamics converges to A, our process also converges to A with high probability. It's not a problem. Do we have the stabilization of the interaction term? For this, we can use the result of Aleksian and Kurzman of 2010 that shows that our mu t converges globally to some attractor.
Yeah, my impression that they proved not a weak conversion, but something like Wasserstein distance conversion, something more strongly.
There is a result for Wasserstein distance conversion. Yeah. There is. And we actually use it in the paper.
Okay.
Yeah, so this guy converges to the attractor. The question is, what is attractor? The attractor is the solution of this guy, which with sigma goes to 0. Actually, here sigma is assumed to be square root of 2. If you just take normal sigma, it will be a Gibbs measure. It will be 2 over sigma square. And with sigma goes to 0, you can show that rho infinity, your attractor, it is actually close to delta A, because it will be something like this around A. And then with sigma goes to 0, it will become closer and closer. So we can control our interaction term. How to get exit time? The same. We just introduce a coupled process. We take the coupling. We have all calculations. We have the result that our distance is bounded by some constant that goes to 0 when sigma goes to 0. So the exit time will be the same. We have this theorem that was published in Yesaya. Okay. So then we pass to something more general. We don't want to assume V and F to be convex anymore. So we consider the following assumptions. First, V and F are regular. This is a normal assumption. Gradient f, gradient v are Lipschitz continuous, normal assumptions. Gradient f is bounded. This is something that's is not very normal, but we had to assume it for a very technical reason. It is very technical. We just had to assume it. But I will tell you afterwards why it is not that restrictive. Okay, I have to tell you right now. The thing is that the domain is bounded, and now we can consider self-interacting diffusion, where you have interaction with the past of the process, with the previous path of the process. And since we are inside the bounded domain, we don't care what is happening outside. So actually, you can change f however you want outside. So you can make the gradient f to be bounded. It is not a problem. So the set of assumptions A2 considers what is this domain G. Yes, bounded regular domain with only one point of attraction that is stable under this guy as before, and something more. So here, I think the assumption A we may be able to prove using the previous assumptions because it seems natural. I think we couldn't prove it immediately, and then we didn't want to bother. What it says is that if you, these guys, since we assume A to be a strong attractor, it should be convex around point A. So here we say that not only it is convex around point A, but also if you change delta A by some measure mu that is close to delta A, here I write it in this way. In the paper, it's written in the
Please say exactly what you mean by mu approximately delta function.
It is close in Wasserstein 2 distance.
Wasserstein distance, of course. Yeah.
Wasserstein 2. We did everything in Wasserstein 2 distance.
Okay.
Yeah. Yeah, so we still should be convex. So if we perturb delta A by a little bit, then it still should be fine. Also very technical assumption. So we have some obvious problems. First of all, we don't have any convexity. Thus, we cannot anymore use coupling methods. At least it is not obvious. We don't have any more control of the occupational measure after some time, because even intuitively we know we are in a multi-well potential. Yeah. So we assume that if sigma is small, most of the time we will spend near the bottom of the well, but until exit time. But what happens after exit time? We just jump to another well, and then we spend some time there, and we jump to another, to another. So actually, here it is different from the first paper. We cannot anymore use results of Kurzmann and Krebsen, because we just know that it is not true that mu t is that mu t converges to something close to delta A. It will not be true. Okay. We have to think about something else. Also, there's another problem. It is non-Markov process. So even if we want to apply Freidlin-Wentzell theory, kind of do the same thing for us, it is not immediate. As it turns out, it is possible, but it is not immediate. Non-Markovianity we can solve. We can solve by introducing a different initial condition. So notice how in self-destructing diffusion, our process depends only on the past of the process, but also on the time where when you start. So actually, what you should know to uniquely continue the path is the point where you start in, the time that we spent in the previous path, in the previous parts of our process.
Okay, I guess for you, M is the previous path before you start observation, yeah? M.
Where's M?
Previous history of the trajectory.
Exactly.
Before this, you start observation, correct?
Yes, exactly. So here, if you see we kind of put all our initial condition into one variable that we call bold x here. That is a triple of T0, mu0, and x0. And here, these are just projections on each of the axes. T is the projection on time on the first variable, M is projection on the second variable, and P is projection on the third variable. So yes, Mx stands for the previous, where the process was before. Tx stands for how much time did it spend there. And Px stands for where do we want to continue our process from. Good. So we did kind of Markovization. Now we have to do something with this. So yeah, here just a plan how to prove it. We should prove large deviation principle for generalized problem, for this one, for generalized process, sorry, for this one with general initial conditions, and try to restore the logic of Freidlin-Wentzell theorem. This is what we did. So here you see the theorem that states that self-attractive diffusion with generalized initial conditions satisfies large deviation principle with the following rate function.
Where is sigma in the rate function? You divide by 4 sigma squared or something.
There is no sigma in the rate function because sigma is the parameter that goes to zero.
Yes, correct. Like in Wentzell theory, you have f dot minus drift squared. Okay.
Exactly. And here you have the same. Because
the signal formula of the Freidlin-Wentzell type. Okay.
Yes, this is actually, it is not that hard to show. What you have to show is that your trajectory of Brownian motions map to the trajectory of the process in a continuous way. Then you know large deviation principle for Brownian motions that is perturbed by a parameter sigma.
Okay, what I have a follow-up question. You can look for exit point in two ways. You can start, you have your potential, you can start with your potential and say, this is minimizer of your expression that you showed previously, or you could take minimize the integral of rate function over the trajectory up to exit point. Can you prove it is the same?
Yes. In the gradient case, it is the
theorem that these two procedures coincide, correct? Or not?
Yeah, it's not a theorem. It's an example.
Observation.
Yes.
Observation.
Yes.
These two definitions coincide. Okay.
Yes. It is not that hard to prove.
I see.
Okay, so we proved the large deviation principle. That gives us the solution of the first problem, first convergence towards point A. As I said before, our process should follow the trajectory of the deterministic process, the one where sigma is just equal to 0. And we can control the level of deviation of this process from this line by using large deviation principle. So we can show that there exists time t, rho stabilization, we call it, such that the probability that we are further away from point A than rho, so rho is just the parameter that shows how close we are to the point A, it is equal to 0. It goes to 0 when sigma goes to 0. Okay. The same goes for the occupation measure. So we say that if sigma is small, then in constant time, we converge towards the point A and we stabilize around it, such that our occupation measure and the process are close to A and delta A respectively. Okay. Stabilization of the interaction term. Well, here it is harder than that. It is very technical, but we could prove it. We could prove it using large deviation principle as well. So we introduced the first time, we introduced time gamma, which is the first time when our occupation measure moves away from this ball of radius rho around delta A. Okay, so we can say destabilized. And we can prove that this will not happen before exit time, or something that is bigger than the exit time that we assume. Here, one is taken, you can take any parameter you want. What is important is that we should not destabilize before we leave our domain. Mu t should be close to delta A. So we prove this. This gives us the stabilization of the interaction term. And how to prove exit time? Well, there is, I mean, we need to prove exit time, but there is no need to consider coupling with the Ito process. Well, first of all, we cannot do it because we are not convex anymore. Using the same techniques as in TUGOV 2016, we could not prove that they're close. But what we did in this paper is that we just restore all the logic of Freidlin-Wentzell theory for self-interacting diffusion. All the steps of the proof, all the lemmas that had to be changed were changed. That's had to stay the same. We remade them for our non-Markov case. And we got this result. So, which states that the same, the exit time is exponential, where the h is the height of the domain. The height includes f, which is the interaction term, and also we have exit location results.
Ну, вот ученики Фрейдлина, они любят еще... Okay, I speak in English. Freidlin students, they also like to write asymptotic for moments of tau.
Yes.
That's standard in this company.
Yes.
Not only, but also automatically, always in these cases, they would present you asymptotics of any moments.
Yeah. We cannot prove asymptotics of the moment.
Of course, it's easy, but it will do no harm for your thesis.
No, it is not. It is not easy to prove.
So you cannot prove asymptotics for the moment. So
no,
I think they believe this is more or less straightforward. If you have the Wentzell-Freidlin situation, you should be able to write asymptotics.
I will explain you why. Because here we control. You see this minimum between the two. We control our occupation measure until exit time or until some big time, but not forever.
I understand. But it's a technical problem. I'm sure it's not a big deal.
I wanted really to put we call it Arrhenius law. This is the asymptotics for moment of the exit time, and I couldn't because of this. Okay. Because you control here your law only until this guy, but what is happening after that you don't know. I think I can prove one of the bounds. I think either upper bound or lower bound. I don't remember. Lower bound, I guess. So I can prove the lower bound for the expectation, but not the upper bound. Because okay, it is actually simple. The lower bound should follow from the Markov inequality from this thing. This is very simple. It's true. But for upper bound, no, I couldn't do it. Okay. So I can continue. We can generalize a little bit our assumptions for self-interacting case. As I already said, that we are inside the bounded domain G. So, and we are in the case of self-interacting diffusion with interaction with the path. So we don't care what is happening outside of this domain. So we can assume gradient V and gradient F to be local ellipses, because if they are local ellipses, they are ellipses inside. gradient f, whatever. If it is not bounded, that it is bounded inside the domain, we can change it outside however we want. But instead, we have to put some growth condition to still have existence and uniqueness of the process. Okay. Moreover, we can relax the fact that G is bounded. Because of this, because of the exit location results, we know that whenever we exit on the lines that's on the boundary of the domain on the level set of this guy of v plus f dot minus a. So we will if whenever we exit from the domain, we will exit alongside this level set. But then what is happening outside of this level set, it's not very interesting, even if it is inside domain G. So actually G is not bounded just because G may not be bounded just because the level set is bounded. This is what is important. Exit cost is constant. Okay. So we have to assume that this guy is bounded. Okay. So yeah, I have some time. Let us talk about self-stabilizing the diffusion now, which is McKean-Vlasov case. You remember, yes, that this is our process as always. But here mu as sigma is the law of the process, not the occupation measure as before. So the assumptions that we took were the following. We assumed V and F to be regular as always. Gradient F and gradient V and gradient F were assumed to be local Lipschitz and having at most polynomial growth. So most of these assumptions are taken from the paper of Erman and Keller and Petman. If you remember, I told you that in the beginning they studied their diffusion process in the general case, but exit time they proved for convex case because they couldn't prove for general one. But for the general one, they did a good job of proving existence and uniqueness of the process, which we just want to use.
Sorry, yes. What means the assumption A is a minimizer of V? What do you want to say? What is A? Where is A here?
Where is A here?
What does assumption mean?
This assumption means that that A is no, it's not a minimizer. It's not a minimizer. It's a local. It's
I think the point where the invariant measure will concentrate depends both on V and F. That's how I understand the matter. Why you take only minimizer? If you want to find the point of concentration, it depends not only on V but also on F. So I don't quite understand what you want to say here.
So A should be a local.
What is A? What is A?
A is a point. It's a local minimum of.
Well, assumption A is a minimum. This is definition of what you want to say. So the denote by A minimize of V. That's you want to say.
Sorry,
the assumption.
The assumption is that A is a local A. It is in RD. It is a local minimum of V.
Okay, so the denote by A local minimum V. Okay, no question asked. Okay, you can denote it. Yes.
Yes. As before, as you remember in the previous A, it was.
But if you want to consider the point of concentration, I think it would believe both on V and F. You can't say it only depends on V. That does make sense for me. Okay. Carry on. Okay.
Okay. So yes, V is convex at infinity. It was also an assumption that was used by Erman and Keller and Petman to prove existence and uniqueness of the process. this was also used somehow. We don't know why they used it, but it was used to prove existence and uniqueness. We don't use rotational equivalence anywhere in our techniques. Yeah, G is a bounded regular domain. A is a point of minimum of V, and yes, and G is stable. Okay. So, how do we proceed? For the first convergence towards A, we use large deviation principle. We use large deviation principle that was proved in this paper of 2008. In particular, they said the following thing. So if we have the gamma t, that the solution that is the solution of this guy, well, you can actually guess in the large division principle. You always guess what should be in the rate function, because this is the trajectory of the process that corresponds to the case where sigma is equal to 0. If sigma is equal to 0, let's look at the process. If sigma is equal to 0, what should be the law of the process? The law of the process is just delta in the point where we are right now. This is the law of the process, because we start in a fixed point. Okay, so the law of the process will be always Dirac delta, which means that this term disappears, just 0. So only gradient V plays a role. So this is how you guess the form of the rate function in the large deviation principle. So, but this is a theorem that they proved that if we take gamma, that is the solution of this ODE, then the process xt satisfies the large deviation principle with the following rate function. Here you see, instead of mu t, instead of the law of the process, we put the deterministic trajectory of the process, which is gamma t. Okay. So, which means that, yes, that's we know that the deterministic process converges towards A because we assumed it. And we know, but due to the large deviation principle, that we will be around this this path that converges towards A. So we have the first convergence towards A. What is about the stabilization of the interaction term? Well, here we don't have convexity, but what we can do is that we could improve a coupling method. It turns out that you don't need convexity actually to use the coupling techniques. Why? I will try to explain. So we assume our functions to be regular. We assume that A is the stable attractor of V, and of V plus F convolution with Dirac delta A of this guy as well. Which means that the second derivative of V plus F convolution with delta A at point A should be positive. I should not say this because we are in RD, but this function should be convex in some neighborhood of A. Let us use this fact. What we can say is the following. We know that if sigma is small, our xt converges towards the point A. Let's start to couple our two processes from.
Okay, but just to be sure that I understand you correctly, by integral, by convolution gradient f and delta, you mean integral gradient f of y minus a, yes? Correct or not?
No, there is no integral.
Okay, this is convolution is integral usually.
Yes, but if you integrate with Dirac the delta, it's just minus.
Okay, so this f yt minus a, yes?
Yes, exactly.
Okay.
Yes. Yeah. So after the first convergence towards A, we can start to couple our two processes. And if we are in the area where V plus F minus A is convex, then we know that by convexity, these two processes get closer and closer together. We know it. Then whenever they deviate from there, using Lipschitz assumption on gradient V and gradient F, we can control the spread of two processes from each other. So whenever they're close here, they're getting even closer. Whenever they leave, we can control it. Now we just have to know how many times they leave this area and for how long. But for this we know, because this is an Ito diffusion. And we can use large deviation techniques to show that the number of excursions is no more than some exponential of order sigma, and that the length of the excursion is not bigger than some constant t. For this guy. But what about this guy? But you remember that we control the spread. So it is enough to start close enough here that the spread does not overcome the fact that yt comes back. So then whenever yt comes back, we know that xt also came back because we know that it happened in a constant time t. So this is how you can prove that the two processes are close to each other without using convexity globally. You just use convexity around A. You say whenever they're close to A, they're getting even closer. Whenever they deviate from A, the spread is controlled and they're coming back fast enough for them not to get far away from each other. So this was the core of idea for the proof of the coupling method in this case. So this is what we proved. That under the assumptions above, there exists eta, such that for any kappa greater than 0, I should have said that it is rho, because before it was always rho. So kappa is rho. The supremum between them to be greater than this distance, kappa or rho, goes to 0 with sigma goes to 0. For which time? T sigma stabilization is the first time when our law stabilizes around delta A, but S stabilization sigma is the first time when it destabilizing, okay? What you can prove from here actually is that S stabilization sigma is actually should be greater than this guy, because greater than this guy or the exit time, because we know that yt exits before this term. This is what Freidlin-Wentzell theory tells us for Ito diffusion, and yt is Ito diffusion. We know that yt exits before this time exponential of 2h plus eta over sigma square. We know that yt exits before this time, which means that xt should also either exit before this time. Yes, it should also exit before this time. Okay. So this is the theorem that was proved. It is in my thesis. It is not published yet. We are preparing the paper now. So we could prove Kramers type law, which is the same, H is the same as before, and we could prove the exit location result as before. So I think I'm going to finish here with the summary, what was done. So 3 things were solved. First, self-interacting exit time problem for self-interacting diffusion in convex case. It was solved using already existing techniques. It was not a very hard job, yet it had to be done. Second, what we did is that we consider self-interacting diffusion in general case, where neither confinement nor interaction are convex. And we solved these results using large deviation principle and restoring the logic of Freidlin-Wentzell theory, which is kind of unique because I don't know any works that maybe they exist, but I don't know them that consider exit time for non-Markov processes. So here we could do it. Yes. And second, we proved exit time for self-stabilizing diffusion in general case, which is also nice because it was an open problem for a long time. And we used it, we solved it using improved coupling method that's I was just told you about. So yeah, these are reference, and thank you for your attention.
I would like to make a comment in Russian.
Yes.
Прежде всего, поздравления, Ашот, потому что за те 4 года, которые прошли с тех пор, как звучил, вы сделали очень большой, действительно очевидный прогресс. То есть, примите мои поздравления.
Спасибо.
Вот. Потом, значит, ну, конечно, работа очень хорошая, конечно, накидать там 2-3 десятка, значит, замечаний тут ничего не стоит. Вот, значит, но я бы все-таки советовал, если до публикации вам, ну, до диссертации фиг с ним, а до публикации все-таки доказать это несложно, что динамическая система имеет единственную точку притяжения. Это не rocket science. Это, в общем, упражнение. А без этого все-таки это выглядит как-то странно. Ну и мелкие замечания кидать, конечно, тут очень много можно. Но это как бы совершенно не тот факт не подчеркиваю, что это очень хорошая работа, конечно. Если вы хотите более подробно, вы можете отдельно со мной связаться.
Да, хорошо. Потому что, может быть, то есть проблема в том, что мы предполагаем...
Конечно, это несложная лемма. Это, конечно, детский сад, да. Ну, что, как это можно такое писать?
Нет, сейчас я просто не очень понимаю, о чем именно речь.
Ну, я вот смотрите, еще раз. Вот,
Да.
в самом начале у вас было уравнение. Значит, вы в него подставляете ваш фикс-point. Вы получаете уравнение, что градиент v фикс-point равен минус градиент f в нуле, потому что у вас xc минус xs это обе неподвижные точки, там 0 будет.
Да.
Ну, и, конечно, доказать, что там есть единственное решение
Градиент f
при условиях, это, конечно, это не такая большая история, там, это просто упражнение. Вот. Это несложно. Я вам советую это написать. Ну и вообще так немножко понятно.
Сейчас я не очень понимаю, то есть нужно доказать,
хорошо, давайте,
что есть...
хотите, зачем мне позвоните, я вам прокомментирую, да.
Хорошо.
Ну и вообще обратите внимание, надо понимать, что начальная задача исходная, она, конечно, не об этом была. Вот там серьезные люди зубы поломали, они не смогли сделать. Это вот был Крис Роджерс, это был, конечно, Дэвид Уильямс и Джеймс Норрис. Это очень 3 серьезных человека. Они не смогли сделать задачу. Они пытались, они что-то напечатали, это modified node intersect book они хотели сделать. То есть non-intersect diffusion. То есть modified diffusion, в которой запрещены самопересечения. Это очень такая задача, классическая задача. Вот, они думали, что вот если вам взять такой последний потенциал, в который все сильнее и сильнее в нуле, так сказать, уходит до бесконечности, и как бы в пределе они как бы имеют там сингулярность, которая запрещает самопересечение, то это можно как-то в каком-то пространстве там обработать эту штуку. Но они это сделать не смогли. Это были очень, очень сильные люди. Но это задача до сих пор, по-моему, осталась так и нерешенной, мне кажется. Вот. Ну, в общем, обратите на это внимание.
Хорошо.
Хорошо, спасибо.
Спасибо.
Да, спасибо докладчику. Кроме Марка Яковлевича, еще кто-нибудь хочет спросить что-то? У меня, к сожалению,
Maybe also in English,
раз 30 прерывалось, интернет неустойчив. И Yeah, but I just tried to explain that I have many problems with internet, and I reloaded the presentation 30 or 40 times during your talk, so it's difficult for me to have a general impression about what is going on. But some things I received also. What about non-constant sigma? Is it known something for such tables?
Non-constant sigma. Yes. So
yes, but I also ask something. Who want to ask?
Non-constant sigma. What you can do is that you can take a sigma multi. So non-constant sigma. Yeah. So for example, in Freidlin-Wentzell theory, they do it for non-constant sigma, but still you should have the parameter in front. So you have some sigma that is the parameter that goes to zero multiplied by some function that depends on.
And then with respect to this parameter.
Yes.
Okay.
And may I ask one more question?
Somebody wanted to ask?
I wish.
Yes.
Yuri, yes.
I'm Yuri Everbuch from
Please.
Moscow, Ekaterinburg. And
Please.
Yeah. Thank you. My question is close to the one put by Professor Konakov. What is about the case when we have, say, two systems? One is stabilized in some point, and another, it is some perturbation. Can we prove such kind of result for more general case? For examples where V is not a gradient of some potential, but we have only some stable state for more general dynamics, and we perturb it not with some kind of Brownian motion, but probably with more general system that includes, say, Markov chain jump-like processes and so on.
So if gradient V is not gradient, but something more general, just a function B from RD to RD, then it is relatively simple to use our techniques to generalize. Actually, we will do it. I think we will do it in the future paper that we plan for McKean-Vlasov diffusion. So this is not a big deal because our techniques, they do not use the fact that gradient V is a gradient of some function. You need it only for explicit form of H here. You see, for example, in this theorem, you have explicit form of H.
And may I ask a question about your technique? Could you use Lyapunov function here, or it is useless?
I do not know.
Okay, because I now read a lot about Lyapunov function, and I thought that probably you could use it here. But I'm not sure, it is only a guess.
Yes, I also don't know a lot about Lyapunov function. I know that it was used for self-interacting diffusion, where you have interaction with the past, to show convergences. I think of. No, I should not go there because I'm not very.
Okay, thank you very much for a brilliant presentation.
I have a question about the possible application of self-interacting diffusion.
Yes.
Typically, with self-interacting diffusion, you can imagine that you can approximate numerically nonlinear Gibbs measure with just a simulation of one pass. And with potentially an application of your result about the exit time, you can, in the case where you have, I don't know, a double potential, say more or less at when your diffusion is very small, you will be close to one of the two wells or no. So the question is, do you think that you will be able to replicate what your result, not for continuous time, but for discrete time or Euler scheme related to your model?
Discrete time, but cannot you have? I mean, if you have Euler scheme, you know the convergence with the number of
At small time or at finite time, you have convergence. And if you are globally convex, you have also uniform convergence of the Euler scheme.
Okay, I see.
But
for discrete time, I don't know how to do it, because for us it involves a lot of calculus.
There is no equivalence of the Freidlin-Wentzell method for, I don't know, perturb Markov chain or something like that. Perturb Markov chain, perturb gradient descent.
There should be something there no that I'm aware of. But will it be? I mean, it depends on what you mean by. I guess so. I guess that there are exit time results for discrete time processes. I'm sure of it. Whether it is a modification of Freidlin-Wentzell theory, I'm not sure. Probably they use some other techniques. Probably. I don't know.
Okay. Now it may be interesting to have really this Freidlin-Wentzell. Well, the self-interacting system is really instead of approximating your nonlinear Gibbs measure by a particle system from a self-stabilizing, you just simulate one pass.
But
with
I have an idea. If sigma is really small, you can use the same logic. You can say that your earlier scheme, it sits around the point of attraction most of the time as the process itself. And then when they deviate from the point of attraction, they deviate for no more than fixed time t until they exit the domain. So each time they deviate, you can control the distance between the two. And whenever they're close to point A, but they're close to point A. And then they jump together to another well and they do the same thing. You see what
Can you imagine Kramers type law as the one that you have for the Euler scheme?
I think so, yes.
The same exit time, everything works the same.
I mean, if my logic is correct, then yes. The logic is the following: that you have one point of attraction. Your process converges towards this point in constant.
It's very
yes. Yeah, I think Valentin Dmitrievich wanted to say something.
Yes, Valentin.
Okay.
Okay, we'll come back. Okay.
Okay. So if you have one point of attraction, your process converges to this point in constant time. So in constant time, you control the distance between your earlier scheme and your process. So they converge together. Then if you can prove that your earlier scheme sits inside there for a long time with your process, then whenever your process leaves from the small ball around A, it deviates. We can prove that there exists time t, which is constant, it does not depend on sigma. There exists time t such that the time that your process spends in the annulus between the boundary of the domain and your small ball here is bounded by this time. And this is a constant time. So you can control the distance between earlier scheme and the process within this time. Then they come back together. And this is how they do. They live together, they come back together. They live together, they come back together. And you don't have to control the distance between the two forever, just for this time t that they live and come back. You see? And then they do it like this for exponentially many attempts, and then they leave.
I see the idea, but there is no, you don't need, for instance, the distance between your Euler scheme and your self-stabilized, self-interacting diffusion. The distance is uniform in time. You just need that for a short period of time, they are together. Because if you are,
but your process leaves your ball of point A, it leaves it only for fixed time, and then it comes back.
yes, okay.
Yeah, so if this guy leaves it for constant time, for constant time, yes, for fixed time, then your earlier scheme also leaves it for fixed time, because they do it together. You can control it.
Okay.
Then they come back, but around point A, they are close to point A, and around point A, we're convex. So it is not that they stay close to each other, they just stay close to point A.
Okay, I think I understand the idea.
Yes, I think it is doable until, so with our techniques, it's doable until exit from the well. But what happens afterwards, for now, we don't know how to think about it, how to approach it. But until the exit of the well, I think it should work.
Okay, okay, interesting. And just a small question about the smoothness of V and yeah, okay, Valentin wants to ask. Valentin?
Yeah, the connection is very bad. We cannot hear you.
Maybe asking the question in the chat.
Yes. Yeah,
Okay, my question was, maybe it's quick, but how much can you go down with the regularity of gradient of V of gradient of F? Is it a question of defining the exit cost?
That's a good question. No, I think with single, no, I think there are a lot of things. And now I'm not, no. I think there are lots of things that will break. I think there are a lot of things that will break. I mean, we use calculus a lot. If it is not, if it is only one point of singularity.
Maybe
Yes. No, I think there is a big delay. That's why he.
Yes.
I just want to.
Yeah.
We hear you, but very, very badly.
With Euler is doable.
Is doable. Okay.
We heard that with Euler scheme and doable.
Yeah.
Well, maybe he said not.
Or maybe this question can be discussed with Vincent. Sorry.
Really very difficult problem with scheme.
Can you repeat, Valentin?
Problem. With and so, but it's to get something for this. Since let's do domain, and it's not done up to now, I think.
Okay. Well, maybe we can discuss that, or you can discuss Ashot with Valentin. There is really trouble with the sound.
Okay,
Valentin.
I continued.
Yeah, we can continue it. Okay,
Wait,
so
I'm here, but in several seconds maybe I will be out, and again
yeah.
up, jump up. Okay.
Okay, thank you, Ashot, for your response.
In principle, I said something, but sorry.
Валентин Дмитриевич, задержка у нас, поэтому мы плохо слышим.
Okay, I think maybe for me it's better not to say something, because I cannot finish my sentence even.
Okay.
More questions? Comments? Okay, so if it's not the case, let's thank the speaker for
Thank
interesting
you very
talk.
much.
Well, we finish now.
No, yes.
Okay.
Okay.
My
Thank you,
internet is
Ashot.
very unstable, so I prefer to.
Yeah. Okay. Thank you. Thank you for inviting me.
Thank you. Bye-bye.
Спасибо. До свидания всем.
Спасибо, Ашот. Пока.